Hi, everybody. Good morning. My name's Jen Leone. I'm the Chief Sustainability Officer at HPD. Welcome to this Climate Ready Buildings training. It's been a long time coming, but we're excited that it's finally ready. Today we'll be presenting along with our partners on this effort, Stephen Winter Associates and the New York City Accelerator, who are the ones giving the presentation, but also want to thank the Mayor's Office of Climate Environmental Justice, the Building Energy Exchange, and a couple other folks that were instrumental in getting this off the ground, our friends at Enterprise, and also a special shout out to Curtis and Ginsberg, who allowed one of their projects to be featured throughout the presentation. Exciting news, this Climate Ready training is not just a training. It was time to be released with HPD's new design guidelines. Stay tuned. We've promised that before the end of January 2023, our preservation design guidelines will be released, and we are on schedule for that. And thanks to everybody who contributed. And following in a couple weeks after that, we will be releasing our new construction design guideline updates. The bulk of this presentation talks about the items in that. And stay tuned. We will be releasing our guidelines in conjunction, finally, with a really cool new construction pilot. I'm going to turn this over to my friends, but we'll be on the chat answering questions.
Excellent. Hello, everyone. I am Kelly Westby, and I'm the Managing Director for Building Operations, Decarbonization, and Efficiency at Stephen Winter Associates. Like Jen said, we're partnering, working with the Accelerator program to provide technical support for the program for the city. And so we're presenting on behalf of the Accelerator. I'm with my colleague, Leanne Harvey, a Senior Sustainability Consultant at SWA, and she'll be talking in a minute too.
Morning, everyone.
So we'll go through some logistics first. It is a 3-hour course. We'll focus on the integration of resilient and high performance design strategies. And that's what we're calling this Climate Ready. So achieve New York City's goals for energy efficiency and carbon emission reductions. We want to mitigate current and prepare for future climate risks and generate efficient, safe, healthy, and of course, affordable housing. We will look at some housekeeping. So we know it's a little bit long. Don't worry, we will have a couple stretch breaks throughout the training. The training is recorded, as you'll note on the screen, for future use. And if you do have questions, please feel free to continue typing them in the Q&A as they pop up. We'll try to get to all of them, but likely we'll have to follow up with some of them later on for, we'll release a frequently asked questions list and send it to everybody who's been involved. And we will use the poll questions throughout. So just a quick note that you do need to answer all of the poll questions in order to get full credit. So pay attention and monitor those poll questions, and you'll see them throughout the presentation today. The session is going to be broken up into a few different parts. So we have the intro, talking through it right now. Then we'll give you a little context. So the greater context of climate change within New York City. Then we're going to look at how to design a climate ready building. We look at it in 2 parts, kind of the higher level design strategies, and then get into the specifics. We'll take you into the deep dive for about an hour. Then part 3 will focus on implementing that climate ready building. What does that integrative design process look like? And then we want to explore it through the lens of a kind of concepts in action. So we're going to take you through that case study that Jen mentioned, beach green dunes. And then, of course, we'll conclude with some points for hopefully everyone to take away with today. After you complete the training, we hope that you're able to summarize New York City's climate policies, understand what the climate ready building strategies are at a high level, and then be able to apply that, especially the integrative design process in your project, hopefully tomorrow. Before we dive in, we're gonna get started with a quick poll. So remember, you do have to answer them. So we'll just get a temperature on the room. What is everyone's profession? You can answer on the poll that should start to appear on your screen. Do we have a lot of architects, engineers, contractors, developers? All right, great. We're getting some good participation early, so I'm glad you aren't sleeping yet, and everybody seems to have their coffee already. We have a lot of architects, no engineers, so I get to be maybe the only one on the call. Contractors, a couple contractors, a lot of owners and developers, and a few consultants. Feel free to type your, I'd love to hear what specifically you're working on. Type in the chat, what's your name, what's a project you're working on, what's your position, and then we can get a good idea with who's in the room. Excellent. I'll turn it over to my colleague to give you that broad context.
Great. Thanks so much, Kelly. So this might be a little bit of a refresher for folks in the room, but we just want to start high level and really look at climate change, because that's what we're talking about when we're talking about climate resilient design. So as you all likely know, climate change is caused by greenhouse gases released from burning fossil fuels like coal, oil, gas. And higher concentrations of these greenhouse gases in the atmosphere result in a warmer planet, altered weather patterns, and more powerful storms. The Intergovernmental Panel on Climate Change, or the IPCC, is a group that's assembled by the UN to monitor and assess all global science related to climate change. So you'll see a lot of their assessment reports come out. And the most recent assessment report states that if global warming exceeds 1.5 degrees Celsius in the coming decades, we can expect more severe storms, flooding, heat waves, and shorter cold seasons. But even if we limit warming close to that 1.5 degrees Celsius, we would substantially reduce, but we cannot eliminate projected losses and damages related to climate change. So we have to prepare for how we can be resilient to those changes. So in New York City, we're already feeling the impacts of climate change. I, for one, am really missing the snow this year. I know that's not everyone's take, but 2021 was the Northeast's third warmest year since 1895. We are seeing patterns of warming in the region. Annual temperatures in New York have gone up about 2.4 degrees Fahrenheit since 1970 and are projected to rise between 4 to 6 degrees by the 2080s. Higher temperatures also mean extreme heat and longer heat waves. In 2080, we can experience up to 87 days above 90 degrees and 6 heat waves per year, which pose severe health risks. More Americans die from heat waves every year than all other extreme weather events combined. So we want to test your knowledge a little bit here for our next question. What percentage of New York City heat stroke death occurs due to indoor heat stress in buildings? All right, seeing diversity of answers here. Looks like we have 58% participated. All right, let's get up to 85%. All right, well, it's looking like most folks are leaning towards 37%. But in fact, it's actually 71%. Shocking, I know. And there are quite a few folks, about 30% of the room, who did get that answer correct. So people die from heat stroke inside of their homes because they may be living in poorly weatherized homes. They may not have air conditioning, can't afford air conditioning, and have chronic illnesses that force them to spend more time indoors during heat waves and can't seek the cooling that they need. So the increase in temperature also means more moisture is held in the air, leading to increased rain, snow, storms. So overall, Average annual precipitation has increased across New York State since the 1900s and is expected to continue to increase. 2019 was one of the US wettest years on record, according to scientists from NOAA. And by the 2050s, average annual precipitation may increase as much as 13%. And according to the DEP, the Northeast experienced an over 70% increase in heavy precipitation from 1958 to 2010. That's greater than any other region in the country. And these frequent and intense rain events lead to flooding, which leads to costly damages to homes, roads, bridges. A NYSERDA study estimated that property damage losses from flooding have cost over $7 billion from 1960 to 2014. And we're also experiencing sea level rise. Per Flood Help New York, sea levels in New York City are rising nearly twice as fast as the global average. So again, we're going to test your knowledge here. How much do you think sea level has risen along New York's coast since 1900? All right, getting some answers coming in. See if we can get a couple more folks to answer. Just take a guess. We're not testing, you don't have to know the answer. Just want to see what you do know. All right, so most folks actually are, we're tied between 8 and 12 inches. So the correct answer is 12 inches, just slightly over. So, you know, a little over a foot. But by 2080, we could see sea level rise by nearly 7 feet. So these rising sea levels lead to growing storm surges, again, increasing the flooding risk from rain and storm events. Since 2014, HPD has built or closed 371 projects, 60% of which are new construction within the 2080s floodplain, which is why climate-ready design is so important for future projects. So to reduce current and future impacts of climate change, we must take immediate action. And as you can see, buildings are the leading source of greenhouse gas emissions in New York City. And they're also an important line of defense for the climate impacts to come. So how do we change our practices in building use and construction to reduce those greenhouse gas emissions? Before we dive in, I just want to make sure we've defined some key terms that we hear thrown around a lot. So decarbonization, simply means reducing greenhouse gas emissions. But when we talk about electrification, this involves replacing fossil fuel power technologies with technologies that are powered by electricity. So when it comes to buildings, this means replacing furnaces and gas ranges with heat pumps and induction cooktops. And finally, beneficial electrification is used to ensure that electrification provides the most benefits and makes economic sense. So you wouldn't want to swap out a gas boiler for an inefficient electric system that increases energy bills and just isn't good overall for the folks that are using them. So with that in mind, let's take a look at how New York is applying these strategies to the building sector. We'll talk through strategic policies, codes, and standards that are listed here, which impact the affordable housing sector. So starting off, the New York City Mayor's office has played a key role in shaping the city's climate policy. In 2018, Bloomberg released a strategic plan entitled Plan NYC with a focus on growth, economy, climate change, and quality of life. And building on that work, Mayor de Blasio released One NYC in 2015, a strategic development plan focused on principles of growth, equity, sustainability, and resiliency. And this plan included initiatives to ensure all New Yorkers have access to safe, secure, and affordable housing, achieve carbon neutrality and 100% clean electricity, and strengthen communities, buildings, infrastructure, and the waterfront to be more resilient. And in 2013, Mayor Adams is expected to release a climate action plan, which will prioritize environmental justice. The city launched a program to provide technical assistance to building owners to take action towards reducing their buildings' carbon emissions. This program has evolved over the years, and today it continues to offer free guidance to any privately owned, new or existing building over 5,000 square feet. It's a great resource for navigating the requirements and identifying financial incentives. And we will hear more about the New York City Accelerator at the end of today's presentation. So I'm sure many of you are familiar with the Climate Mobilization Act passed in 2019. This includes a suite of local laws, and we'll cover those laws that are particularly important to HPD funded buildings. Starting with local laws 92 and 94. These require that all new buildings and any existing buildings doing roof work must install green roofs or solar PV. HPD has a carve out in the policy which excludes affordable housing projects until 2024. So to take advantage of incentives, HPD created the solar where feasible policy, requiring solar on affordable housing only when it's cost effective. So teams must submit a solar feasibility analysis to HPD and install solar where it's deemed financially feasible. Though each building and solar array is unique, HPD reports that a typical payback period is less than 10 years. The cornerstone of the Climate Mobilization Act is Local Law 97, which establishes carbon emission limits in buildings over 25,000 square feet. So buildings are categorized based on their use type, and each category has its own carbon intensity limit. Emission limits become increasingly stringent over time and are subject to hefty fines for non-compliance. Buildings that include affordable and rent-regulated housing are not exempt from Local Law 97, but may be treated differently under key articles. So depending on key factors such as the number of dwelling units, as well as the rental or ownership structure, and affordable housing is subject to specific emission limits, requirements, and key deadlines. So most HPD projects are subject to Article 321, which requires that the covered buildings can prove by May 1st of 2025 that they either did not exceed their carbon limit for the 2030 to 2034 timeframe, or that they implemented the applicable prescriptive energy conservation measures that are listed in the policy. So this is a useful flow chart from HPD to help owners determine their compliance pathways, and we'll be sure to share a link for that following the presentation. Besides the CMA, Local Law 154 is another law targeting carbon emissions and effectively bans the use of gas in buildings in all new buildings and gut renovations. So this starts in 2024 with a phased rollout that starts with low rise, and then they add taller buildings in mid-2027. Affordable housing projects are on an alternative timeline with delayed compliance deadlines. So buildings with 50% or more affordable housing will also be given until 2026 to comply for low-rise buildings and 2028 for taller buildings. One thing to note here is that electrification of water heating systems aren't mandatory in the first phase and have additional time to comply. And at the state level, the Community Leadership and Climate Protection Act of 2019 outlines a path for New York State to reach net zero greenhouse gas emissions. So this law requires that New York State add significant renewable energy and energy storage capacity. And specific targets are to achieve 100% zero emission electricity by 2040 and reduce emissions at least 85% below 1990 levels by 2050. So this is why electrification of our building stock makes sense, because we're also cleaning the grid at the same time. So in addition to these policies, Energy codes are getting more stringent. So two key codes are the New York City Energy Conservation Code and the New York City Stretch Code. These two codes are closely aligned on efficiency measures such as insulation and lighting standards. And future iterations will just continue getting stricter. So starting in 2025, the city's energy code for buildings will require a specific level of energy performance that is more stringent than baseline code and moves us closer to something like passive house performance levels. This is a significant change as teams will have to utilize performance-based energy modeling rather than prescriptive measures to demonstrate compliance. The policies we discussed address how we use energy in buildings, such as using energy more efficiently and moving away from non-renewable fossil fuels to more sustainable energy sources. But the climate resiliency guidelines and Local Law 41 of 2021 are focused on driving resilient design so that New York City's building stock can weather changing conditions, growing stresses, and extreme weather events. The guidelines translate future-looking climate change projections into technical guidance and help ensure that city capital projects constructed today will be prepared for worsening extreme weather decades into the future. So there's a 5-year pilot program to apply these design guidelines on 35 capital projects, including 3 HPD projects. And by 2026, all city projects must meet a stringent set of requirements that will certify their preparedness for extreme weather threats. More and more private developers are electing to design for resiliency, going beyond code to ensure their buildings are ready to withstand climate change. Excuse me. And the Unified Stormwater Rule and release of the Stormwater Manual updates and aligns water quality requirements in the city's combined sewer drainage areas with requirements in separately sewer drainage areas. This manual provides technical guidance for developers, designers, and engineers who will work with DEP on stormwater permitting. This is required for projects that disturb 20,000 square feet of soil or create 5,000 square feet of impervious surface. So next we'll cover HPD policies and guidance for resilient and energy efficient affordable housing. So starting with Enterprise Green Communities, this is a national green building standard designed for both new construction and rehab affordable housing projects. And their 2020 criteria has Certification Plus for pursuing high performance certification and a greater emphasis on health and wellness via alignment with the WELL building standard. So as you may know, EGC criteria are organized into specific categories such as integrated design, site improvement, and operating energy. Some criteria are mandatory while others are worth optional points. But HPD projects must go beyond the national criteria and comply with the New York City overlay, which shapes EGC to address the city's unique needs and goals. So the New York City overlay requires projects to achieve more points for certification and make certain criteria mandatory instead of optional. And we'll dig into all of that today. For new multifamily supportive housing and senior housing, HPD funded projects must follow the HPD design guidelines for new construction, which establishes the criteria to evaluate proposed developments. The 2021 guidelines, as Jen mentioned, are being updated as we speak and will align with HPD's climate goals and will include all electric building requirements, new future-looking resiliency requirements, and new criteria for health and well-being. And finally, to support beneficial electrification, HPD has developed policies for electric heating to protect residents and ensure performance. So the electric heating policy and tenant paid heat policy enables tenant paid heating in limited situations that does require HPD permission. It does restrict resident paid heat on projects with vulnerable residents like seniors or formerly homeless, only allows for high efficiency equipment, and does refer to new heat pump utility allowances. All right, so Another question to test your knowledge based on what we just heard. How many days of over 90-degree temperatures are we likely to face by the 2080s? All right. Got 61% participated. Let's see if we can get it up there. All right, looks like most folks were paying attention. Love to see that. So it's 87 days. I referenced it earlier. Most folks in the room did get that correct. And another little quiz. How many feet of sea level rise might the city face by the 2080s? And again, just a reminder, if you have questions that come up, feel free to use the Q&A feature in Zoom throughout the presentation. All right, again, it looks like most folks did get this correct as well. It's 6.75 feet. All right, great job, everyone. So now we're going to dive into part 2, designing a climate-ready building. So as professionals and practitioners in the building industry, we need to design, construct, and operate buildings that mitigate and adapt to climate change, meet New York's current and future ambitious climate laws and goals, and meet HPD's metrics for safe, healthy, and affordable housing. So we can achieve that by integrating resiliency and high-performance design into affordable housing projects. So what is a high-performance building? What is high-performance design, and how is it different than business as usual? So high-performance buildings reduce energy consumption and carbon emissions while ensuring the health and safety of occupants in the energy grid. So more specifically, they're utilizing highly efficient all-electric equipment, which minimizes or eliminates the reliance of fossil fuels. They're super airtight, minimizing heat exchange, maintaining comfortable, even temperatures, and they have balanced ventilation, providing fresh air, reducing the heating and cooling load through energy recovery. So what is a climate resilient design, and how is it different than building business as usual? So resilient buildings can withstand and recover from extreme heat, extreme storms, flooding, and more. They use future forward climate information to maximize impact and ensure that the building continues to withstand evolving climate conditions such as sea level rise, precipitation, and rising temperatures. And as we previously mentioned when talking about enterprise green communities, the New York City overlay has additional resiliency focused requirements and opportunities to earn optional points. So resilient and high performance design strategies come together to create a climate ready building. So climate ready buildings are healthier, they're safer and more efficient. They lower greenhouse gas emissions, are affordable and future proof. So let's dive into what each of those means in a little more detail. So here's another little quiz for you. Roughly what % of energy use comes from heating a conventional building? All right, got 63%. Get a couple more people to answer. Looks like we may have capped out here, but it's close. So most folks know that it's not going to be 10 to 20%, but the answer here is around 50 to 55%. And this is based on a study of homes looking at 86,000 homes. And so this chart here really shows that breakdown. So climate-ready buildings use significantly less energy than conventional buildings. This shows that breakdown between a passive house building and a conventional building. So you'll notice that the passive house total energy consumption is cut by more than half, and most of that comes from heating. Because climate-ready buildings consume less energy, they are also much less likely to be at risk from accelerating energy costs or spikes. The green row in this table shows percentage energy cost savings for 6 case studies. They also have significantly lower greenhouse gas emissions. So this chart here is from a study from SWA comparing 6 passive house buildings with conventional buildings, passive house in green, conventional in gray. So greenhouse gas emissions from the passive house buildings are significantly lower than the 2030 limit set by Local Law 97, while the conventional buildings go above that limit. So this means that passive house buildings will not face fines in 2030, and all electric passive house buildings will avoid fines in 2050. Climate-ready buildings are healthier because they provide fresh filtered air, resulting in better indoor air quality. This chart shows the results of an IAQ monitoring study for several schools in the UK. Conventional buildings have higher CO2 spikes, while the passive house buildings maintain healthier levels. And we all know how uncomfortable a drafty window can be. Climate-ready buildings limit the amount of heat transfer, keeping the space conditioned to an appropriate temperature. So this image here shows an infrared scan of a block, and the passive house on this block has almost zero heat transfer through the envelope. Climate-ready buildings are safer than conventional buildings because they maintain livable conditions even during periods of power outages. So if anyone could take a guess, how many days do you think one could survive during a winter blackout in a passive house building? I could launch that next poll. All right. So we got 70% that participated, and most folks did get this right, 7 days. We have answers across the board, but 7 is the correct answer. So Urban Green Council modeled indoor temperature changes during a blackout for different building types and found that in winter it takes 7 days for a passive house building to become uninhabitable, while a conventional building only takes 2. And finally, climate-ready buildings are future-proof. They're safer and have lower risk from climate impacts, resulting in the potential to save money as well. This graphic shows that elevating your homes can lower insurance premiums. So HPD has already developed some climate-ready buildings, all of which are passive house certified. So we've got the Knickerbocker Commons in Brooklyn. It was the state's first 100% affordable multifamily passive house building. 475 Grand Concourse in the Bronx. We have Mapes Ave Apartments also in the Bronx, which features an innovative solution for window ACs that allows them to be closed and thermally insulated during the heating season. and Sendero Verde, which has over 700 units of affordable housing and is the largest fully affordable passive house building in the world. So a couple more questions. Oh, it looks like Jen has, Jen, you have your hand up. If you want to chime in, feel free.
That was an accident, but I did want to note that the graphic on the previous slide is maybe the single biggest argument for doing high performance building, the safety factor.
Yeah, absolutely. Thank you. All right, so a couple more questions. So before we asked you about the heating in a conventional building. So now, do you remember what the percentage is for a passive house building? All right, we got some answers coming in, looking good. Maybe we get a couple more. We're at 63%. All right, so most folks got this correct. Good job. 5 to 10% is the answer here. So we went from 50, cut it significantly with a passive house building. And now we'd love to just have you list, one attribute of a climate-ready building that stood out to you from what we just discussed. And as you're doing that, again, just a reminder, use the Q&A feature. We'll answer your questions throughout. We are right at 10, so we're going to take a quick little break, 10:10. So we'll come back at 10:15. We're going to take a 5-minute break right now and let you grab your coffee, check an email, and then join us at 10:15.
All right, we hope everybody had a moment to get your coffee and a little bathroom break, and we're going to jump right in to section 2B. And just a reminder again, as I've been typing in the chat, that make sure to answer those polls. Whether you have the right answer or not is not the biggest deal, but we want your participation. Also, keep in mind that keep the questions filtering through on the question and answer. We'll either type an answer right in there to you, or we will update them live if we can. So jumping right in, building off of what we learned in the previous section, we're going to take a more detailed look at how resilient and high performance design measures come together to create that climate ready building we've been talking about. So in this section, we'll discuss specific design strategies, and they kind of fall into these 8 key building components that we have cute little icons for here. So we have the site, the envelope, heating and cooling, ventilation, water, lighting and loads, resilient and renewable systems, and of course, materials. I'm sure you're familiar with some of these, but we're going to go in and assess these design measures that you'll need to consider for your own projects. Some of the strategies might be business as usual for you in particular, but hopefully you'll find some new ones with us here today. As you assess the design strategies, you'll want to consider all of your own project specifics. So first, we'll just dive right into the site. We have specific site design strategies that can greatly improve the resiliency of a building and the safety of its occupants as well, particularly during extreme weather events. The location of your building will directly influence its exposure to climate risks. For example, a project may be at greater risk for flooding if it's located close to a coastal waterway or in low-lying areas, of course. Even a project that is currently at a low risk for flooding might lie within a future floodplain and face increasing risk of exposure over time. So we need to think about the site design as a key line of defense from external stressors. We want to consider floodproofing, stormwater management, heat island mitigation, and we'll kind of go into these 3 concepts in a little bit greater detail. We'll also go into the exposure screening tool in more detail in section 3. For now, I'll just give you an overview of the strategies. So floodproofing aims to protect the occupants and to reduce or eliminate floodwater damage to a building. So what we mean by this is we want to elevate residential uses. We want to elevate that critical equipment such as HVAC, means of egress. We want to elevate that all above the future design flood elevation. Natural flood mitigation features like berms or living shorelines can also help. We can also provide wet or dry floodproofing strategies, as well as deployable flood barriers as kind of a method of that temporary strategy. Teams also need to account for future flood elevation to make sure that the building is prepared for extreme weather events that continue to build over time, unfortunately. For stormwater management, we want to reduce impermeable materials as much as possible. These materials can really exacerbate flooding as the water runs quickly into and then overloads the system. We want to reduce hardscape, add permeable paving, and plant areas like green roofs, bioswales, rain gardens. Permeable paving, as you can see here, allows the stormwater to naturally be absorbed into the ground through porous hardscape materials. Bioswales and rain gardens allow vegetated areas, and those areas are designed specifically to collect and manage that stormwater. Floodproofing and stormwater design strategies work in concert to protect the building from increasing precipitation and tidal inundation, both of these issues. The design strategies are particularly relevant for New York City because in New York, we have a combined sewer system, which means that both sanitary and stormwater flow together. And that overflow can mean that dirty sewer water from your toilet goes right into your local waterways when it rains. Stormwater management can help reduce the instance of combined sewer overflow and keep our waterways cleaner. And of course, this third strategy we want to touch on is the heat island mitigation. So structures like buildings absorb and re-emit the sun's heat more than a natural landscape. So urban areas often experience higher temperatures, which can be unsafe for residents and taxing to the building's cooling systems. Green roofs with native or adaptive vegetation can help manage and reduce ambient temperatures at the roof. And there's also co-benefits of reduced stormwater runoff, like we talked about, increased biodiversity, and of course, a lovely amenity for your occupants. Teams must account for this additional structural need early in design to make sure that it's not an added cost or add-on later. Using native or adaptive plant species also helps reduce the water demand since they're native to the New York City climate. We also want to look at reflective roofing and paving. So reflective, light-colored site materials obviously reflect the light and don't absorb the heat as much. We want to select the materials, though, that are appropriate for the space. So will the space be in uninhabitable spaces, or will they be amenity spaces? We want to adjust the brightness so that it's appropriate for the use. You can also provide shading with trees or trellises, solar canopies, as you can see here. They can provide additional comfort for amenity spaces. Both green and cool roofs can reduce air conditioning demands and maintain a healthy and comfortable living environment. And we also want to reference back that local law 9294 that Leanne mentioned. Integrating green roofs into the building design can help comply with those requirements if solar PV is not feasible in the site. And actually combining the green roofs and the solar PV, we can discuss it a little bit more later, but combining the two can enhance the performance of both systems because you provide shade that helps the plants grow, and you also lower the ambient temperature, which increases the efficiency of the solar panels. You'll see throughout, for each building component, we're going to review the strategies and the alignment with 2020 EGC criteria. So I won't go into too much detail because it's a little bit of a repeat of what I've been saying so far, but you'll see that each of the strategies might have benefits, either energy, resiliency, health, or a combination of all three. And all of these, energy, resilience, and health, all of these combine to create that climate-ready building. So now we'll dig in on the envelope. Of course, a high-performance envelope can reduce energy use and infiltration and increase the occupant comfort. It also helps keep occupants safe from the impacts of climate change. The building envelope is one of the most important systems because it moderates that transmission of air and moisture in and out of the building. A robust envelope that's highly insulated and airtight is fundamental to reducing the HVAC loads as well. That improves in comfort, and it allows occupants to have that place to shelter in place during or after natural disasters. We want to make sure we have that robust, tight envelope. And so we want to consider, we'll dive into the different strategies that we want to consider to really optimize for that performance. While these high performance envelope will require more oversight, there's going to be more details that you need to make sure you get right. And so you'll need that oversight like inspections, you'll need performance testing, maybe blower door testing throughout construction to check and correct for any inconsistencies. But it will really benefit your building over the long term. The envelope really stays with the building for a long time. One way to really optimize is to keep it simple. I say this a lot, and I know that simplicity can be a little boring sometimes, but we can actually make really exciting, simple designs, and they make it easier to reduce the amount of mistakes made in the field and save cost overall so that we can build even more affordable housing. Complex forms create all these opportunities for confusion or issues to arise in the field. The building orientation also helps or can hurt in order to take advantage of passive design. And then we also want to take a look at providing the optimal window to wall ratio. The window to wall ratio is the total fenestration area divided by the total wall area. Heat loss and gain through the windows has a significant impact on the thermal comfort of the building occupants. Energy code has prescriptive maximum window to wall ratio if you're following that prescriptive path, and that'll depend on whether you're following ASHRAE or New York City Energy Code. So consider all of these elements: the facade orientation, what code building standard you're under, and your project goals to make sure you're designing an appropriate strategy for your windows on your project. So of course, for I'm sure you've heard us talk a lot about this, continuous insulation and mitigate your thermal bridging. Those are sort of two sides of the same coin. So we want a robust envelope, insulation continuity, but there's going to be opportunities throughout the entire facade where things will have to be attached, whether that's your cladding, whether you have parapets, equipment dunnage, facade attachments. And so consider what thermal break options you have so that you can minimize that heat loss through those penetrations. So consider thermal brake pads, autoclaved aerated concrete, and other insulative structural components. There's a lot of components on the market right now that maintain the structural integrity of the assembly overall, but minimize that energy transfer. So conventional windows and doors often have poor thermal performance, and if you don't install them properly, there's substantial air infiltration around these penetrations. The problems can be solved if we provide high performance windows, of course, and doors, and make sure that they're well installed, airtight, and of course, they're insulated, thermally broken. So we want to look at a low U factor. A U factor indicates the thermal transmittance, or how much heat is conducted. The lower the value, of course, the better the window insulates. Pay attention to the assembly U factor, so the frame and the glazing combined. It's possible to have a high performance glazing, but poor framing that reduces the overall thermal performance of the window. And most of the time from the manufacturer, automatically, you're going to get just the glazing performance. You have to ask for the assembly U value. It is a requirement in the energy code as well. While high performance windows might cost more than the standard windows, there will be significant energy savings. And high performance windows don't have to be triple pane necessarily. We'll get into that in the example project as well. Also make sure you're choosing a climate appropriate solar heat gain coefficient. Solar heat gain measures the amount of solar energy that will pass through the glazing. The lower the solar heat gain coefficient, the less solar heat is transmitted and the greater shading ability. Recent energy code updates include more stringent requirements for fenestration, both in terms of U factor and SHGC. And the performance requirements for glazed assemblies, including windows, doors, and of course skylights, will likely become more stringent with future code updates as well. Work with your team to make sure you're understanding the optimal U factor and SHGC for your glazed assemblies based on the facade orientation, based on the code and building standards, and based on what you're able to do with your construction team on site. Thermally broken assemblies are important. Just like the structural thermal breaks we just talked about, thermally broken windows and doors will include insulated barrier that helps to minimize heat transfer through the frame. And one of my favorite topics, the continuous air barrier. Of course, the gaps in the building envelope significantly affect the energy performance and result in drafty, uncomfortable, and cold or too hot occupant spaces. Improving the air tightness around the envelope, including the windows and the doors, mechanical and plumbing penetrations, etc., that all saves energy and increases the comfort. Teams have to utilize an air barrier continuity plan. It's required anyway, but if you take it seriously, then it can really ensure that any of the gaps in the air barrier materials, particularly at transitions, are going to be identified in advance, and that you don't have to come up with a solution as it pops up in the field. Thorough air sealing is important to prevent air infiltration. So additional air sealing at all penetrations, within the envelope, around windows, doors, HVAC, plumbing penetrations, of course, just to name a few. And in the New York City climate zone, we really are looking at the vapor permeable air barriers. So designing for the appropriate construction for our climate zone. And I love this slide because it shows how important the envelope is. We look at energy, resiliency, and health, and the envelope impacts all three. Implementing these strategic envelope measures can really help your building achieve the critical criteria in the operating energy category and achieve points for greater efficiency if you're looking at programs that are above code like Passive House. Heating and cooling. So we'll discuss a few of these strategies in detail. In high performance cold climate buildings, when we're talking about carbon reduction, we really want to think about all electric space conditioning systems so that we can reduce those carbon emissions and provide efficient heating and cooling to occupants. The performance of a mechanical system is contingent on the integrity of the building envelope. So that's why we talked about that first. Smaller capacity and more efficient systems are critical for electrification, particularly to manage the demand on the grid and the demand charges of your building during peak periods, peak load. So we'll get into the heat pumps in a little detail. I know it gets a little bit on the technical side, but wanted to give everybody a baseline overview of heat pumps. So it's a critical technology, of course, for electrifying heating systems. They don't generate heat, but instead move heat from the outside where it's cold to inside. Heat pumps can be, in that way, several times more efficient than a standard piece of combustion equipment, which is about 85% for a standard boiler, or maybe higher for condensing boiler if it's actually condensing. We'll be reviewing three types of air source heat pumps, three types of split air source heat pumps, I should say, as well as a package terminal heat pump option, and then of course, ground source heat pumps. There's a lot of considerations when choosing the right heating system for your project. So I'll just name a few. Utility billing. So in New York City, heat is often paid by the owner, but heat pump systems provide heating and cooling. So determining the utility split can be complicated but important consideration. Cold climate technologies. For New York City's climate, it's extremely important to understand and select for cold climate technologies that can operate efficiently at low temperatures. Thermal zoning. So certain systems will require proper zoning to ensure efficiency and to make sure that the system is operated as intended. Outdoor space, roof space might be required for outdoor equipment. This could be on balconies, on the actual roof, sometimes located on walls. We also, when we're talking about heat pumps, need to think about refrigerant and refrigerant leakage. Refrigerant is a very high global warming potential substance. And so leakage is a huge concern when we're talking about climate ready buildings. We want the installation contractors to perform the proper pressure testing, evacuation procedures, and startup so that everything is properly installed and documented. We also need to think about condensation, that indoor units will require condensate drains for cooling and the outdoor units for draining when they defrost in the winter. So this is just an additional consideration that you may need. And then maintenance. So certain systems may require additional maintenance or maybe just a different style of maintenance that your team might not be used to. And you may need access to the apartments to diagnose those issues. So we'll get started with those three split system types, starting with kind of the most simple, the mini split heat pumps. So these are typically a single zone, or what they call a one-to-one. So it's just one indoor unit and one outdoor unit. And you can kind of see the connection on the upper right-hand side, the indoor unit providing facilitating the heating and cooling into the space, and connected to the outdoor unit that's pulling the heat from the outside. Typically, the tenant will pay for heating and cooling for this type of system, but it can be wired to the house meter so that the owner can pay. It's typically used for buildings less than 7 stories or those with balconies for outdoor units because of their refrigerant line length limitations. It's only, there's a limit to how far away the indoor unit and the outdoor unit can be from each other. They tend to be lower cost than the VRF alternative, which we'll get into in a minute, and require less training to install, and they have a greater contractor base that's used to installing them. And sometimes in the field, they can have actually a higher COP than VRF based on what we've tested and seen in the field. Some consideration though, maintenance is often a concern with decentralized system because you have a lot of equipment in the building. You have more outdoor units, and so one outdoor unit is needed for every indoor unit. They need to either be hung on exterior walls, or you need enough roof area, which we don't always have in New York City. And using that roof space will mean that you might not have availability for current or future PV system. So the next most kind of complex split heat pump would be the multi-split. So this is where you're serving multiple zones. So maybe there's 2 or more indoor units served by 1 outdoor unit. That's kind of shown by the diagram on the upper right there. And as you can see, the indoor units can serve different rooms. It could serve different apartments, although it's not typical, and it could be connected to 1 outdoor unit. These units can either be ducted, meaning there is ductwork within the apartment, or ductless. Maybe there's a head on the wall that you might be used to seeing. Typically, the tenant pays for heating and cooling, can be wired to the house meter again, and they're typically, again, for buildings less than 7 stories. It's still a residential sized system, and so the line length restrictions are a little bit smaller than the VRF counterpart. They tend to be lower cost than VRF, similar cost to one-to-one, and slightly more complex startup than the mini splits. The maintenance can be a concern. You might have multiple zones down if you just have 1 outdoor unit down. So that's one thing to consider. There's a little bit less built-in resiliency. And lastly, we look at that VRF that I've been alluding to. So the VRF is a multi-zone system, multiple indoor spaces served by 1 outdoor unit. It's typically a much larger system, 6 tons and up. And you can have either a heat recovery system or heating only, cooling only system. The heat recovery system allows you to have 1 outdoor unit that's serving some indoor spaces that are in heating and some indoor spaces that are in cooling. The pros are that it's more efficient, you have better control, and you can meet the thermal needs of different apartments at the same time. The cons are that it needs to be carefully planned out to actually realize the efficiency. It is more costly, and it does have a little bit more complicated nature in terms of the controls and how to change over. VRF is available with heat recovery and without, but a lot of manufacturers do state that you should be using heat recovery models for multifamily buildings, even though we do see a lot of multifamily buildings with heating only, cooling only systems. The owner typically pays for this type of system since it's grouped together, but you can bill tenants based on submetering, which is done through an added component from the manufacturer. This is typically used for taller buildings, as the systems can have longer refrigerant lengths than mini and multi-splits we talked about. So some considerations to think through for this type of system: you consolidate the number of rooftop units you need or outdoor units you need, but you have multiple dwellings or spaces affected by the same system. So if something goes down, you do have that greater impact. It is also much more complex in terms of the piping and the controls and the proper installation and testing and startup is really required. That goes for everything. Testing and installation and startup is important for all systems, but the more complex the systems, it can get, all of those stages become more complex. And for the next solution, this is almost the other direction, the most simple. It's packaged terminal heat pumps. It's unitized, provides heating and cooling to one room, and typically heating or cooling will be on the residence meter automatically. But there are some options in development to make sure that we can have a solution where the owner can pay for the heating, which would be for affordable housing projects in New York City. The models provide, you can have a model with a heat recovery ventilation kit on it. And so the considerations with this unit is there's no ductwork, so that reduces the amount of equipment in the field. All of the refrigerant is contained within the unit, so you minimize the risk of leaks. There's no field installed refrigerant piping. You can retrofit, you can provide an option for retrofitting PTAC buildings. So that is nice with and in the future, if a solution comes out with a lower global warming potential refrigerant, it should be easier to swap out one of these units than a unit that has refrigerant lines running everywhere. You need to make sure with these systems that you choose cold climate options. There's a big difference between the typical PTHPs on the market and the newer cold climate solutions. And unfortunately, there aren't as many of the cold climate versions available right now. These units also require condensate drains at every unit, so something to consider. And then, of course, ground source heat pumps. These are extremely efficient with COPs from 3 to 6. So it can be almost, over 2 times the of an air source heat pump. Ground source heat pumps work with a underground heat exchange loop and heat pump. Ground source heat pumps work with the underground heat exchange loop that's installed underneath. And then the heat pump within the space provides heating and cooling to multiple different apartments. Typically, the owner will pay there for heating and cooling. And we can also use this loop to provide domestic hot water. It's not suitable for all sites, though. There is a New York City geothermal or ground source kind of feasibility mapping tool that we can post there in the link. And Jen is always reminding me to refer to HPD's electric heat policy documents. So making sure, I've been mentioning how they can be configured. That's from a technological standpoint. In terms of whether to bill the tenant for heating and cooling. From a technology standpoint, there are different options open, but always for an HPD project, you have to refer to the electric heat policy documents before assuming that you can configure in a certain way. So that's been one of the complex parts of heat pumps for now. And here, so this system analysis kind of takes us through each of the units we just discussed and gives you a chart to break down the technologies for multifamily applications and show you each of the considerations for the system type. And we'll provide the chart as a supplemental resource. I believe we even have more details in some of the documents for the accelerator information, so we can provide those around. Of course, no matter what system you choose, but again, particularly for those more complex field installations, it is important to ensure that the commissioning agent is incorporated early in the design and is involved throughout the construction process and really even into occupation to ensure that the systems are designed, installed, and are operating properly. Full disclosure, though, I do have a background in commissioning, so I may be biased. And of course, the EGC criteria. Just like the envelope design strategies, implementing these heating and cooling measures can help a project achieve the criteria under the operating energy category. And so you can achieve points for greater efficiency over the baseline. And these strategies will also help you achieve the energy performance in passive house or living building certification. And now we'll jump right into ventilation, which is another exciting topic. The balanced ventilation with energy recovery will improve indoor environmental quality because we're providing fresh air while reducing emissions and energy use compared to the traditional ventilation systems. Ventilation is required in all buildings, but business as usual in New York is that exhaust-only systems that frankly don't work well or don't work at all, unfortunately, in some cases. Without proper ventilation, a variety of contaminants build up inside the apartments and inside the building. And these are things like outdoor allergens, pollutants, dust, and moisture. The contaminants can lead to mold, mildew, rot, and can trigger respiratory illnesses like asthma. And they can even start to cause structural damage. This type of damage is actually the leading driver of insurance claims, a leading driver. As building envelopes become tighter and ventilation systems become even more important. So particularly in an ultra tight envelope like a passive house buildings where you're designing to that really tight standard, you need to consider the proper ventilation. But balanced ventilation or exhaust and direct filtered fresh air is best practice across all buildings. Balanced ventilation can control moisture and pollution better than an exhaust-only system. So we're going to focus on energy and heat recovery ventilators because that really is best practice. They recover the waste heat to precondition the incoming air. So you provide the indoor air quality you need with reduced demands on the heating and cooling equipment. This efficiency enables engineers to specify much smaller equipment, and that becomes more economical on the heating and cooling side. The heating and cooling might be required for a conventional, sorry, let me try that again. The efficiency gained from the heat recovery will allow you to reduce the size of your heating and cooling system. HRVs transfer heat only, and ERVs transfer heat and moisture. Keep in mind that for ERVs and HRVs, but really for any air supply system, you want to select high performance filters with MERV 13 or more. That's recommended by ASHRAE, particularly in locations with PM 2.5 concentrations that are high, like near a highway or something like that. There are two options for ERVs and HRVs at a broad scale. So we can look at centralized or decentralized systems. For decentralized systems, this is also known as a unitized system, and it serves individual apartments. So you might have one ERV or HRV per apartment, serving all rooms within that apartment. The in-unit ductwork will penetrate the exterior walls, so you end up with a lot more penetrations, and air sealing around these penetrations must be carefully performed. Unitized equipment is often wired to the tenant meter. You do need to change the filters regularly. As we mentioned, the dust and dirt and things will build up over time. And so you will need, in this case, you'll need access to the apartments. That can be challenging, and you also need to make sure that the exhausts and intakes aren't located near operable windows or other kind of code clearances required, like doors, things like that. So that can be a challenge locating them. We also want to make sure that the outdoor air intakes are accessible so that they can be cleaned regularly, at least twice a year. These grills sometimes are hard or impossible to reach from inside the building. For central systems, there's a different set of challenges. They serve multiple apartments through a common exhaust and supply ductwork. And depending on the size of the building, maybe one or more ERVs or HRVs are usually located on the roof. Sometimes if it's a very large building, maybe somewhere in between. Air sealing and ductwork is critical for these central systems. Duct leakage significantly reduces the efficiency of the system and reduces the amount of ventilation or exhaust rates from the spaces that we're trying to ventilate. This can be performed, so air sealing can be performed before the drywall is installed and along the way as the building is being built, and in addition to sealed using an aerosolized sealant like AeroSeal. After the ductwork is installed and complete, you can seal up the ends of the system and blow in a sealant from one end to really get at all those tiny cracks and holes that are difficult to get by hand in the field. Testing, adjusting, and balancing is critical for these systems too, because they're going from oftentimes from the top of the building all the way down. So we want to make sure that they're balanced properly. Sometimes you might have heard of a drive-by tab contractor. You need to make sure you're hiring a qualified contractor who's really testing the flow rates and can provide feedback to the mechanical contractor when something's not working properly. This will also require maintenance, like filter changes, but the filter changes are obviously limited to that rooftop unit, which is much more easily accessible rather than the apartments. ERVs and HRVs are always going to benefit with a balanced supply and exhaust flow. So make sure to plan for equal flows when you're designing the system to begin with. Humidity control is also an important aspect of healthy environments. The ideal range for relative humidity in indoor spaces is sometimes referenced as 30 to 60 or maybe 40 to 60%. This is the range that human health and comfort are optimized and pathogens on the other side are reduced. When indoor air becomes too dry, it can lead to respiratory irritation and increases the risks of viral transmission. I'm sure we've all heard a lot more about that recently. Similarly, when air becomes too humid, it creates conditions for bacteria to thrive. So you get mold and dust mites forming, and that can obviously trigger allergic reactions and negatively impact respiratory health. For higher performance buildings, dehumidification is required. ERVs and HRVs can be used to tackle some of this dehumidification. MEP engineers must evaluate the humidity potential for the building carefully and determine whether additional controls on the ERVs or HRVs is necessary, because the buildings won't perform in the same way as your conventional projects. So implementing these strategic ventilation measures can help a project comply with several energy and healthy living environment criteria. Before we jump into water, I will take a couple of minutes to see if there's questions, anybody wants to speak out loud, or Jen wants to jump in with anything I made a mistake on.
Yeah, Jen, if you wanted to jump in with Sonia's question now, or we can answer it later, whatever you're thinking, Jen.
Sure. I don't know, Sonia, if the question is about how geothermal systems work. I don't want to go into that, but I assume if you're talking about how billing is affected, that is one thing that we don't have a protocol for. We see that typically either the heating and cooling is split out between the building owner and the residents, and or in some cases where the in-unit portion is wired in a kind of complicated way to allocate the heating to the building owner and the cooling to the resident. I don't think we have a straightforward way of doing that yet. It's something we're working on, but I just wanted to be able to answer the question.
Yeah, thanks, Jen. That you spoke to it a lot more eloquently than I did. Thanks for jumping in. All right, we'll continue answering your questions in the chat or live, so please feel free to continue asking them. And we will jump into water. So there are lots of improvements for domestic hot water systems so that we can save energy and reduce the energy it takes to heat that water. And of course, reducing water use in the building will also benefit the city's sewer infrastructure. Remember that overflow going into the river issue. So we reduce water pollution, and we can help, of course, reduce energy and carbon use. As we mentioned with heating, reducing our reliance on fossil fuels is a really important component of buildings, climate-ready buildings moving forward. It will decrease the long-term carbon emissions as we consider all-electric domestic hot water systems. So that's what we're going to focus on first. The types of electric domestic hot water systems are generally boiled down to centralized heat pump systems with storage, that's for larger buildings, decentralized unitized heat pump water heaters, typically for 1 to 4 family homes, and then non-heat pump solutions for specific applications within the building. The configuration of central versus decentralized. So central configuration for domestic hot water system is most applicable for multifamily homes. We have 2 potential options for central systems, air to water heat pumps with storage, or water to water heat pumps served by that ground source loop we were just talking about, or another heat source. Packaged heat pump water heaters are that you can see kind of on that bottom, that typical packaged heat pump water heater, cylindrical looking thing, is most applicable for 1 to 4 family homes. And then there's non-heat pump solutions, also known as electric resistance solutions, that might be applicable for certain applications. So we'll get into those in a second. So a deep dive on the central side. In general, central systems are best suited for large multifamily buildings where individual water heaters would just take up too much space in each apartment, or they might drive up the electrical capacity requirements and create a potential maintenance burden on staff, just like those indoor ERVs, unitized ERVs. And storage is generally needed for these central systems in order to meet that domestic water load in the building, which is highly variable over the course of the day. So 2 heat pump options are available for central domestic hot water configurations. We have that air to water heat pump that I mentioned. The major limiting factor for these is the outdoor space required and the limitation of available products on the market. It really is a newer technology to the US. We typically want to maintain tank storage temperatures greater than 140 degrees to prevent the Legionella growth. This high temperature is most common or most available for models with that CO2 based refrigerant because it can, because of the cycle of that particular refrigerant, can reach higher temperatures. But right now there are limited air to water heat pumps available using CO2 on the market. So the other option is water to water heat pumps, meaning that the heat is exchanged with a water loop. So those systems are often coupled with a ground source heat pump to provide higher temperature hot water. Packaged or unitized systems, such as the heat pump water heaters, are more applicable for 1 to 4 family homes, as we discussed. There are multiple options and products available on the market, and these units, even though they've been available for a long time, we still do see a lot of installation issues across the board. So it's important to consider the installation requirements that you need when choosing these for your project. They need adequate clearance in a space with enough heat gain to replace the amount that the heat pump extracts. So just like behind your refrigerator in your house, it feels really warm. Around these units, the opposite thing will happen. So around the unit, it will feel cold. If there's not enough air to make that up, then you will start to freeze the space around, and that can either cause poor operation of the equipment at best or freezing conditions in the space. In addition, the units tend to be loud, so it makes installing them within the apartments kind of undesirable. An operating unit behind closed doors can actually measure at a noise level of 50 decibels, compared to the recommended 35 decibels or less, which is sort of a standard for high performance buildings. They can also create cold spots when they run, which creates comfort issues in the apartments. The units aren't recommended typically for multifamily applications, particularly in New York, because the dense population makes it really difficult to find adequate spacing. In certain applications, other electric domestic hot water solutions are best suited, better suited than heat pumps. So for point of use water heaters, these are really a great solution if you have a one-off common area bathroom or an office kitchenette. The electric heaters are right there where the installed fixture is. And so you don't have any heat loss along the way. It could also work for tenant fit out spaces and things like that. The solution will reduce the distribution losses, like I mentioned. So in a large central system, you have a lot of the energy consumption of that system is actually from pumping the water around the building and reheating it based on those distribution losses. So since these projects are lower efficiency than heat pumps at the source, and they also require sort of a larger electrical capacity, they're usually used more in these like one-off cases. Besides the actual system that's used, there's a lot of solutions to improve the overall efficiency of the domestic hot water distribution system. So we can look at efficient plumbing layouts, wastewater heat recovery, and water monitoring, and of course, low flow fixtures. So for efficient plumbing layouts, this is actually a really interesting thing. Approximately 30% of the energy use associated with the hot water delivery system is wasted in the distribution losses, just waiting for the hot water to arrive at the point of use. So efficient piping layouts can actually reduce the losses by about 40%, or reduce the amount of time it takes to get to the fixture. So you save both the water and the energy. You can also lower your upfront material costs in some cases, so it can be a win-win. Wastewater heat recovery. So drain water heat recovery systems are designed to capture the heat that's lost from the hot water going down the drain, and it's used to preheat the cold water that enters the building. There are simple off-the-shelf solutions with no moving parts if you talk about single-family homes and even small buildings. So then the application is pretty straightforward. But for wastewater heat recovery in a package unit can be used in larger buildings, and it can really be beneficial, but additional resources and accessories might be required, like a black water tank. So it's something to consider with your design team, but think through all of the design details. Water monitoring and leak detection. So of course we've seen the leak detection requirements in the 2015 criteria of UGC. This requirement was created because it helps teams monitor consumption and be able to respond quickly to leaks and inefficiencies, right away. Monitoring water by fixture or dwelling unit or riser gives you a more nuanced picture of the water consumption than a whole building water meter where you might lose information in the noise. But even though the upfront cost of the added meters, there will definitely be an upfront cost for the added meters. In the field, it will reduce the effort it takes for someone to figure out where the leak is. But they only work if someone actually monitors and pays attention. So it's important to figure out the strategy for the long-term operation. Low flow water sense fixtures. I think most of us are probably familiar with these types of fixtures by now. So the requirement has been around for some time, and we want to make sure we continue to use those low flow fixtures because that will help us reduce the size of our all electric systems if we choose them. If we don't choose them, and we decide electric domestic hot water is not feasible for the building, then we should think about how we plan for electricity in the future, because over time we really are moving towards zero energy, but sometimes we don't have the feasible solution right now. So we need to ensure that the DHW distribution system is properly sized, efficiently laid out, and balanced. This one is easy because it makes sense to do now anyway. We should install isolation valves around the equipment to make isolation and removal easier during retrofit. Again, this helps anyway. The equipment, no matter what it is, isn't going to last forever. And we should choose storage tanks instead of instantaneous for gas-fired plants. If you don't use storage tanks now, leave floor space and structural support for them to be installed in the future. As we mentioned earlier, most central electric DHW solutions will need storage capacity. Factor in extra space for piping, risers, and insulation so that you can run the chases from the boiler room to the outdoor unit, which typically the heat pump will probably be an outdoor unit. Also, leave enough room for your electrical rooms for additional future electrical panels, switches, disconnects, etc. So again, these strategies can help you achieve a lot of the points in enterprise green communities and efficiency, resiliency, and health benefits. So we'll jump into lighting and appliances. Efficient lighting yields energy and cost savings while maintaining a comfortable living environment. So lighting is really impactful for our occupant comfort and health, but also for the energy consumption. Electric appliances also reduce carbon emissions and improve occupant health and safety. So first we want to reduce the load, of course. We can reduce the lighting power density. So the lighting power density is the electrical load of the lighting per area lit, measured in watts per square foot. Many spaces are overlit, meaning that the LPD is higher than needed, which just wastes the energy and potentially can even cause occupants discomfort. We want to optimize the LPD based on the space type, and we want to choose high efficacy lighting, such as LEDs, which are really pretty standard and available on the market today. It's always good to choose the high quality LEDs to work for your project. It's also required by code, but a good practice to take advantage of daylighting. And you want to make sure that any daylighting, automatic daylighting controls are optimized and are set up properly so that they don't just get shut off during, on day 2. Consider back to that window to wall ratio and that orientation and see if you can optimize for the use of natural light in the space where it might be most useful. And be careful to avoid too much glare, which would cause occupants, of course, to close the blinds. And lighting sensors and controls. There are a ton of code requirements around lighting sensors. So using those vacancy sensors, the manual on, automatic off instead of occupancy sensors, keep in mind where different things are required, but also keep in mind what you're using the space for and how to optimize for your particular project. And you got a preview of it, but the electric appliances. So electric or induction cooktops, I don't know if all of you have been hearing a lot about these lately, but there's been a little bit of a, dare I say it, firestorm of information on electric cooktops. They really do a good job of creating a healthier environment for the inhabitants. They also reduce the risk of fire from combustion. Gas stovetops are notoriously contributors to air quality problems. And there's gas leaks, fire, CO poisoning, impacts of respiratory issues, asthma in kids. There are a lot of good options for electric cooktops and clothes dryers. You can reduce your energy consumption with light and also reduce your carbon emissions while improving your occupant health when you electrify your appliances. So some really simple strategies there. All right. So resilient and renewable systems. It's good that I got to this because we're going to take you to the home stretch, and I swear there's a break after this. We'll get you to that in about 10 minutes. So renewable and resilient systems reduce carbon emissions and minimize reliance on utility grids while ensuring the safety of occupants. The resilient systems we want to consider are emergency power, areas of refuge, and access to device charging and broadband, something that you might not even think of. Emergency power to critical loads in common areas. This can allow for heating, cooling, medication refrigeration, Wi-Fi charging. we want to be considering options like efficient generators, islandable photovoltaics, combined heat and power systems, prolonged power outages. HPD encourages the developers to consider resident recreation areas that can be used as a space of refuge that have full backup power with heating, hot water, and refrigeration, and allow folks to shelter in place when available. We also want to consider access to potable water. So during power outages, there may not be the pumping, well, you wouldn't have your pumping available. And so you want to consider how will people be able to have access to water for drinking and sanitation needs. There's a few different strategies, and in New York City, we can often rely on street pressure, but we need to balance finding a location within the building where there's enough pressure, but it's also above the floodplain. So something to really consider within your building and space and how to design for that. This might also be something that's newer to consider, but you need access to broadband these days. Using online learning, teleworking, and accessing telehealth and emergency services, even more importantly in this type of situation. So help close the digital divide by having this access to the technical needs that people need when they shelter in place. Renewables and distributed energy, obviously good for backup power as well. We want to consider solar PV or solar plus energy storage, or maybe if you're not ready for it, just storage ready. So maybe available in the future. For a PV array, install where it's feasible. It's required anyway. And if for some reason it's not feasible, make sure to consider how to include options to design for a solution in the future. So focus on PV. And then just a shout out to HPD has introduced this solar where feasible mandate. So like I mentioned, it is required that solar be installed on all HPD-financed projects as long as it's financially feasible. So storage can obviously help with backup power today or provide just alternative options for demand response in the future. Electric vehicle charging may even be required soon by New York City. So there's currently incentives available through Con Ed, and these chargers can actually be bi-directional. So a car battery could be used to store energy and may be used in times of emergencies. So definitely consider providing emergency power to critical loads, such as through islandable PV systems or efficient generators. And really, you need to consider providing an area of refuge for residents. And our last section here is on materials. Some of you may be familiar with different material requirements from previous iterations. And so we do want to make sure we're careful to select and manage the materials to improve occupant comfort, but also to reduce the building's embodied carbon and minimize impacts on the waste stream. There's a direct connection between materials and occupant health, considering the off gases that occupants will come into contact with and different products that the occupants will come into contact with on a day-to-day basis, as well as carbon emissions. While we focused mostly in this presentation on operational carbon, we need to consider the embodied carbon, or the GHG emissions associated with manufacturing, transporting, installation, maintenance, and disposal of these building materials. So for thinking about healthier materials, and in this section, there's going to be a lot of lists we refer to. So these will all be available later as well. But you have to consider avoiding chemicals of concern. Specify products that have publicly disclosed ingredients, and choose products that minimize human and environmental health hazards. Every day we're exposed to potentially toxic content from the materials that make up the built environment. The first step in ensuring the healthy building occupants is knowing what chemicals we're exposed to and what health hazards might be associated with those chemicals. as practitioners, we are in a position to act on this information and avoid known and potential hazardous materials. Public ingredient disclosures for building materials allow project teams to make more informed choices. There's a growing number of sources for these, and understanding the potential health impacts can make your project even stronger for your occupants and the built environment. So consider Health Product Declaration, also known as HPD, not to be confused with the other HPD. A self-declared list of ingredients in building materials by the product manufacturer. The report discloses contents of building materials as well as their possible human health effects and hazards. These health product declarations are overseen by the Health Product Declaration Collaborative, which is a nonprofit organization that has members from across the building industry, including architects, designers, building owners, manufacturers, and consultants. Declare labels are described, sometimes they're described as a nutrition label for building products, listing its ingredients as well as other key information such as volatile organic compounds and embodied carbon. The Declare labels were launched and managed by the Living Future Institute. Other third-party certifications provide guidance on materials that have been assessed for toxicity, such as ILFI's Red List, which is annually updated inventory of materials and chemicals prevalent in the building industry that are known to be harmful to humans or the environment. UL's Green Guard Gold certification means that the product has been verified to have low chemical emissions, and then Cradle to Cradle, which evaluates a product's impact on the environment. Just as transparency regarding the contents and the toxins available or within the materials is key to optimizing selections for human health, we also need to think about now transparency regarding a product or material's embodied carbon. It's critical to specify low emissions materials and reduce a building's overall impact on climate change. So we want to specify products that have environmental product disclosures. These reports contain information regarding a product's impact on the environment, including embodied carbon. Select low carbon concrete or steel and insulation. Products, these kinds of products, we want to consider ones that have relatively low embodied carbon. So maybe considering mass timber products, such as cross-laminated timber, sometimes referred to as CLT. And these are now actually permitted under the 2021 building code revision. So there's some really exciting progress being made on this front. We also want to select products that have low global warming potential where feasible. So traditional refrigerants, typically, as I mentioned in the HVAC section, those refrigerants have high global warming potential, but there are alternatives. So consider following along where the federal government kind of starts to mandate phasing out of these high global warming potential refrigerants. We will definitely start to see new options on the market. And lastly, those waste streams. We want to manage the waste and also provide recycling options. So providing additional storage for future waste stream options. You want to provide space within the building for that. And then enroll the building staff in DSNY's, Department of Sanitation's zero waste building maintenance training, or free e-cycle and refashion programs. So the materials section can significantly impact the energy use of the building and the health of the building. So we want to implement strategic material selections that help a building comply and earn optional points inherent to that materials category. It can be important to read the documents clearly so that you follow all the criteria, since there are specific thresholds that must be met and documented in order to obtain the additional points here. So as a reminder, the particular design strategy doesn't guarantee certification under 2020 Enterprise Green Communities. You need to, of course, make sure at along the way to consult the 2020 EGC manual, the New York City overlay, and your project team for additional information and guidance. This was just meant as a high-level overview of some of those most important design strategies. So before we get to the break, we have a final question for you, and it's an open answer question. So just what's a new design strategy that you heard about today, or a technology that you heard about that you want to implement in future projects, or maybe at least find out more about? And we'll give you a second to answer that in the poll. It is a long answer. All right. We'll share some of those answers, I think, as folks come back, but we can let folks take a 5-minute break and come back at 11:25. We'll leave the poll open for you. As a reminder, you will get credit for this course, but you do need to answer the polls. So we look forward to all of your answers, and we will see you in 5 minutes.
All right, welcome back, everyone. Hopefully folks were able to take a quick little break and sit back down again, and we're in the home stretch now. So I'll go ahead and jump right in. We have just gone over a ton of key design strategies for what makes a climate ready building. But project teams also need to know how to strategically incorporate these strategies that we learned about. And a key factor in this is utilizing the integrative design process. So we're going to start out with another question. What does the integrated design process mean to you? So if you just want to type that in the poll, we'd love to hear about your experience with it, and yeah, see where folks are. Unfortunately, I'm not sure if I'll be able to see the answers immediately as they're coming in, but we will reflect back on these, and it will definitely inform future presentations. Give folks some time. Looks like maybe not everyone has joined us yet, so we'll just give folks a little bit of time with this question. I would love to be able to see what folks are typing. Let's see, we've got about 36%. All right. Great, thank you so much for answering that. So let's dig into it. So IDP is an approach to building design in which a comprehensive interdisciplinary team collaborates from the earliest stages of design to project completion, from start to finish. It's intended to optimize the input and knowledge of all stakeholders to achieve well-defined project-specific objectives while staying within budget and on schedule. So conventionally, the design and construction process is a bit siloed, which leads to miscommunication. There's a lot of back and forth between teams, which slows the project down and costs more in the long run. But in an integrative design process, there's much more collaboration, there's critical thinking, and an interdisciplinary approach where the team is assembled during the early stages of design and continues. So today we'll focus on 6 steps of the IDP process to help us design a climate-ready building. Starting with step 1, assembling our project team. So as we discussed, in a conventional approach, team members are siloed, designers are developing their scopes independently with relatively limited input from others in the project. But in IDP, this approach empowers everyone on the team to bring their diverse skills and expertise to the table. It also utilizes a dedicated project manager or an IDP facilitator to coordinate the team, to bring everyone together and ensure everyone remains engaged during design and through construction. Step 2 is assessing our climate risk. So as we discussed, Enterprise Green Communities has a lot of requirements that you may be very well familiar with, one of which being the project priority survey. This is required during schematic design, and it guides the project throughout the process and is a very helpful tool for the IDP process. But in the New York City specific overlay, This requires that climate change related risks that we discussed about early on in this presentation, such as heat, precipitation, sea level rise, those are also addressed using the city's exposure screening tool. So if your project is high risk for any of these factors, then you must use the city's climate resiliency guidelines. This tool must be completed during schematic design and submitted as part of a project's pre-build application to HPD and enterprise. And we will get into this tool a little bit later as well. But using those risks and priorities that we've assessed and established, we now have to set our project goals. So focusing on climate risk, just honing into sea level rise, we'll use that as an example. If we determine that the project is high risk for sea level rise, we'll then go to those climate resiliency design guidelines to establish measurable goals towards flood protection. So on the screen, this is an excerpt from the design guidelines that details how to calculate the design flood elevation, which requires you to adjust for sea level rise and your code required base flood elevation. We'll also want to ask, what are our energy performance and carbon goals? Do we want to set above code performance targets? How can we design now to avoid local law 97 fines later? And what are our health goals? Our energy performance and climate resilient strategies have associated health benefits, but do we want to set further health goals, such as earning the EPA Indoor Air Plus certification or implementing active design strategies? And what performance standard do we aim for? So all HPD projects are required to follow the Enterprise Green Communities New York City overlay, which also requires Energy Star multifamily new construction certification. But you can also aim for other standards like Green Communities Plus, Passive House, or LEED. HPD projects are encouraged to use the all-electric Passive House standards, as they're more likely to meet those future carbon targets. Next, the project team will work together to develop design strategies to meet the resiliency, performance, and health goals that were established. One excellent tool and really fun tool of setting those are design charrettes. So design charrettes are meetings that bring together that comprehensive project team that we've already assembled. So these are super helpful from not just the start of the project, but throughout the project to bring all the stakeholders together. They're also great for getting feedback from stakeholders in the community to meet specific goals of the residents that will be utilizing the space. And one thing that I want to note here is that the New York City Accelerator is here to help with design charrettes. So the New York City overlay provides an automatic point if you work with an accelerator account manager to host a design charrette. And if any of the goals that are the strategies identified in the charrette are applied, you can earn additional points. Energy modeling can be used throughout design to compare the performance of different building systems and to show compliance with certification standards. So the type of model or software really depends on the certification being pursued and the design components being investigated. But energy modeling is extremely helpful throughout. They can go through multiple rounds of revision during design. Design or spec changes must always be communicated back to the energy modeling team so that the building's performance projections are accurate and continue to meet those certification requirements. You can also underwrite the projected energy savings for a climate-ready building to take out a larger loan for the project. So on the screen now, these are HPD's underwriting worksheets. And you can typically underwrite 50% of efficiency savings and around 75 to 80% of solar savings. And during design, you really need to outline everything that should be done in construction. This includes all critical things in your design documents to make sure that they happen, such as testing protocols and commissioning requirements. These really need to be set in stone before we get to construction, so that that whole project team is on the same page and knows the order of operations. And once we have that, we head into the build stage. So a really important tool for making sure that, construction stays on target, and, we're engaging with our IDP team are full-scale mock-ups of elements such as the above-grade wall assemblies. These are really great learning opportunities for the general contractor and tradespeople, especially if they've never, used these materials, if these are new materials or techniques that are being used at the site. They really help teams work out any issues in an isolated scenario before it's installed and replicated throughout the project. If we have a lot of mistakes over and over, it's going to add up quick. Some considerations that the energy consultant, commissioning provider, architect, and owner will want to review to make sure project requirements are being met and to weigh in on any questions that come up during these assemblies, these mock assemblies. These photos here are examples of mistakes that can happen in the field when mock-ups are not provided or properly constructed. To meet the air tightness requirements for the Passive House standard, an air barrier inspection and testing plan is essential. So this involves a specialist reviewing plan details, scheduling inspections, and developing contractor checklists. The screenshot here in this example of one of the tools that Passive House consultants use for large multifamily dwelling projects. It's an app for repetitive leakage testing and insulation inspection to make it easier to streamline the process. And then the app generates an issue log, which can be seen on the right side of the screen. So without mock-ups, without an air barrier plan, without some of these tools that are utilized in construction, a lot of issues can happen. So these photos show some of the mistakes that often occur that result in delays and increased cost to fix the issues. So on our left, within the pink, we've got an air barrier plan that didn't include the piping penetration and didn't indicate how to seal around it. So it just wasn't sealed at all. In the upper middle, we have an example of when the energy model did not account for thermal bridging for metal studs. Bottom middle, the contractor looks like didn't complete a mock-up and did not properly install the mineral wool by cutting it and fitting it snugly between the gaps. And the upper right looks like we have a carpenter that didn't cut the drywall effectively or snugly around the penetrations, making air sealing difficult to accomplish. And it looks like the person doing the air sealing didn't do such a great job either. And then the lower right, the drawing showed interior insulation in the wall cavity around the window, but there was no room to install any. The window assembly was thermally broken, but the attachments were not. So depending on the certification requirements, installed HVAC systems, and the performance goals that we established, performance testing might include duct tightness testing for space conditioning, window tightness testing, compartmentalization blower door testing for air tightness of individual dwelling units, whole building blower door testing to verify the air tightness of the entire building. So some things to consider for testing is that open communication is critical. Consultants should communicate scope and expectations with the construction team for all inspections and testing, including key individuals, the installers or technicians needed on site during the testing and during the inspection at each location that will be tested. Failures to, miscommunication, just not laying out the plan can often cause delays. So construction teams should tell consultants if they are not ready for the inspection or testing. And finally, project teams should measure the ongoing performance of the project to verify the design goals are being met and to diagnose and address operational issues early. So a data collection strategy is important for ongoing monitoring of building performance to assess and optimize performance over time. Data can also help owners understand if a system is malfunctioning or if there are any building issues with the meters. HPD projects are required to benchmark through the benchmarking protocol, like all other buildings in the city, over 25,000 square feet. And no matter how the building is modeled, what the goals are, what the expectations for the building performance is, the actual energy performance will depend on occupant behavior and building maintenance. So Enterprise Green Communities requires an operation and maintenance plan and manuals for all multifamily projects. The project's commissioning team should train the O&M staff on the specific equipment they'll have to maintain to improve the longevity and efficiency of those systems. And just as a note, CUNY's Building Performance Lab does offer a 30-hour building operation training that can be incorporated into staff requirements for the project. And resident manuals are also essential. So all residents need to be made aware of the benefits, the use and maintenance of their home's green features. EGC does require resident manuals that highlight building systems or controls that they will encounter when adjusting settings in their homes. And residents should be encouraged to consider and conserve their individual energy use throughout the year. EGC requires that resident manuals also include resiliency information, such as how to locate emergency shelters and cooling centers, hurricane resources, and location of backup power if you're using that design strategy. And finally, lessons learned from design and construction should be incorporated into future projects. The IDP process ensures that lessons learned by the full team filters into the next project. This is why the second passive house is always easier than the first. So to reiterate, the IDP process aligns with specific 2020 EGC criteria, one being that implementing IDP is mandatory for all 2020 EGC. But as a reminder, certain IDP tools such as the Project Priority Survey and the Climate Resiliency Design Guidelines Exposure Screening Tool must be completed for the project's pre-build submission. And again, another reminder, you can receive those extra points in the charrettes and coordination category by engaging the New York City Accelerator. So another open-ended question for the group. Where do you typically see mistakes happen in projects? Have you had any major issues like the photos that we shared? Where do things fall apart within the IDP process? We'd just love to hear examples of those. And while everyone's filling this out, we will tee us up. We're going to go through the IDP process again, but this time with a case study. So we're going to look at beach green dunes. Kelly's going to come back for that. All right, looks like we've got 51% participation.
We may be testing the limits of our buildings with all the precipitation recently.
Yep.
All right, as folks continue to answer, where do you typically see mistakes happen? I guess we'll see that we see them everywhere, of course. But with this, we wanted to dive into a concept, calling it concept in action. So kind of look at all of these different strategies and how they would apply to this specific case study, or how they did apply to this case study. This is a real project. So for the next section, we'll kind of look at this completed building. This is the beautiful building, Beach Green Dunes. It's in Rockaway, Queens. It's a 2-phase multifamily affordable housing development that was part of a neighborhood rebuild after Superstorm Sandy. Speaking of storms. Phase number 1 of this project was a 7-story, 101 unit, and it was 109,000 gross square feet, and it was completed in 2017. So we'll spend this part breaking down the case study by following the IDP steps laid out in part 3 that we just went over, that Leanne took us through. And so the first step, of course, is to assemble the project team. For this development, the ownership was a key driver in pulling together the comprehensive team with various areas of expertise. So Bluestone had been building passive house buildings for 10 years, initially through the Build It Back program. And so they were familiar with that standard. And they knew from the beginning that they wanted Beach Green Dunes to be passive house certified as well. So they added Curtis and Ginsberg to the team. They were brought on board to lead the design. Even though Curtis and Ginsberg were an established and recognized name in the industry, Beach Green Dunes 1 was actually their first multifamily passive house project. So Bluestone looked to round out the team with a set of experienced consultants, including Johnson & Urban, who was the mechanical engineering firm that had experience in high performance multifamily housing projects. And then Stephen Winter Associates, a sustainability and energy consulting firm that provided the passive house expertise and commissioning services as well. Bluestone played actually a dual role in this project as the developer and the builder, and that really helped streamline the overall construction process, particularly, again, since they had experience. With the project team assembled, it was time to assess the risk. So we want to go in and assess the site's risk. We're going to actually try this as an exercise, so bear with us. We're going to drop the CRDG exposure screening tool into the chat. Now, Leanne kind of gave an overview of this screening tool. And Leanne, I think maybe you should be able to drop that link in the chat. And you can, it'll open as a read-only copy. But you can save a copy to your computer, and you can navigate through the document as we talk through it. And so then that way you get some exposure to the exposure screening tool. So once you go ahead and open the link, you can go to the File tab on the upper left, click Save As, download a copy. When you open it up, you should be on that Exposure Screening Tool tab. There's other tabs for appendices and things. So first on this screen here on the left-hand side is heat exposure. It's also kind of the top section of that exposure screening tool, the Excel file. And any other hosts, feel free to jump in if you're just getting a lot of folks in the chat that aren't able to access the tool, but otherwise I will assume everything's running smoothly. So the first question under the risk screening questions, it says, does the facility include new construction or build of the building envelope, HVAC, roof, hardscape, or landscape? And we're going to do this as an example for the Beach Green Dunes project. So we know that this is a new construction project, so we give that yes, a 1. Now we'll skip to the third question. how many annual heat waves are projected? We know this to be 9. I know this to be 9 because we went to section 2A of the guidelines, and based on the project's end of useful life, the corresponding answer was 9 days. Now for that middle question, the question is the facility a neighborhood tabulation area with high heat vulnerability? So we're going to ask you to find this number directly. Go to that health data portal, which you should find the link in your chat. Yep, it was just chatted through to everyone. And go in and pinpoint the neighborhood. I'll give you a little hint. The neighborhood is Edgemere. Now we're going to release the poll. And so that link, you should be able to find the heat vulnerability of Beach Green Dunes, which is in Edgemere again, and type your answer to that question in the poll. We'll update the poll in a second here. It'll give you a second to find the link. There you go. What is the heat vulnerability of Beach Green Dunes? 1, 2, 3, 4, or 5? All right, we got a big mix of answers. I think folks are honing in, finding the link. We have about almost 50% of the folks answered the right one, which is 3. Excellent. So next we look at precipitation. That word we're having trouble with. That's this middle section of the slide here, and it's also the middle section if you scroll down in your Excel file. So does the facility require a new DEP site connection proposal or modification to the existing site plan? Yes, in this case, in Beach Green Dunes, it does, so you can click that yes. Does the site have a history of flooding during precipitation events? You would go to 311 requests and check with institutional knowledge, and that tells us for this project, yes, there has been flooding. And remember above that we talked about Superstorm Sandy affecting the site. And will there be a net increase in impervious area on the site as a result of the project? And that answer again is yes. So now we're going to do another exercise. Finally, we'll look at the sea level rise risks. What is the current flood risk? We're going to ask you to find the city's flood hazard mapper to find this answer. So you go to the link, and Leanne just dropped that in the chat. You'll first have to agree to the terms and conditions. Nothing terrible, I swear. You can navigate to this map by changing the map layers. So in the top right-hand corner, it's going to look like 3 stacked squares. Make sure the flood insurance rate maps for 2015 are selected. And then you search for our site in the address bar. The project site, Leanne just typed in the chat, 4419 Rockaway Beach Boulevard in Queens, New York. So that was the site for Beach Green. So now you can tell us, we'll update the poll. Is there a current flood risk for Beach Green Dunes? Yes or no? Give you a couple seconds to download or to search in the map. It's a pretty fun tool. Or scary, depending on how you look at it. All right, is there a current flood risk for Beach Green Dunes? The answer is a resounding yes, and that is true. So now we go to the next and kind of last. What is the future flood risk? So the under sea level rise now, future flood risk. I'm sorry, still under precipitation. The future flood risk, using that same map, you can actually find the future flood plain with find the corresponding projects, end of useful life. You can find the future floodplain. And we know that this site is at risk for future flooding. Makes sense since it's at risk today. We can see, does the site have a history of flooding from high tide events? From local knowledge and 311 requests, we know that it does. And finally, are there critical access roads that the site will be inundated by future high tides? And again, so, current high tide inundation is a yes, probably future high tide inundation also a yes. And that wraps us up. So the project team got these answers. So for heat exposure, a score of 8, which is a medium. For precipitation, a score of 4, which is high. And for sea level rise, a score of 5, which is also high. And you should be able to see that corresponding on your tool as well. This means that in this case, for this particular project, the climate resiliency design guidelines are a critical component. So the next step in the process, we're going to set up those project goals. The project goals both should relate to resiliency, and some of those will relate to the climate risk, of course, and also performance based on these risks, and energy performance and more. So we mentioned that, spearheaded by Bluestone, the team knew that the project was going to pursue Passive House certification. They established that they wanted enhanced levels of survivability that we discussed in 2B in the event of future catastrophic storms, such as Sandy. The key benefit of Passive House is that there are these high thermal mass and robust envelope assemblies that can help reduce that risk. And so this addresses that site medium risk of heat exposure. And then we mentioned that the site has a high risk of sea level rise exposure. And so the building was elevated to address sea level rise. To address the rainfall and stormwater flooding, stormwater features were explored, including vegetative and site retention strategies. Ownership wanted an environmentally friendly building with relatively small carbon footprint that also had low operating costs. They wanted to go above and beyond and still save money. They ended up choosing an all-electric, efficient heating and cooling system, the VRF system. So once they set these goals based on their risks and based on the intentions of the design team, they were able to kind of jump into that design process from a more informed place. So let's dive into those details. The specific design measures used at Beach Green Dunes. It's worth noting that part of the resiliency pilot through the mayor's office, the project was part of the resiliency pilot through the mayor's office. So design strategies were really identified pretty early, and that really helped them carry through the entire project and not be added costs later on. So on the site, they chose floodproofing and stormwater management items based on the project's location near the coast. The site is composed of actually 67% pervious asphalt, 4% impervious concrete, 29% landscape. They have bioswales with hydric habitat plantings to retain stormwater, and also parking areas that are composed of permeable paving. All of the apartments and mechanical systems and point of egress were elevated above the floodplain. And the habitable floor height was elevated 4.5 feet above the base flood elevation. The climate resiliency design guidelines actually require it to only be 4 feet, so they try to go above and beyond. Entrance areas contain these flood vents, which is a wet flood proofing strategy that allows water to flow through even in an enclosed space. And then they moved that critical equipment up to the roof. Heat exposure risk was reduced by having the white reflective roofing and terrace paving materials, and the solar array, which we'll discuss, of course, later, but it played double duty by providing shade to the area. So some insights that they considered, the combination of these measures were selected to install and achieve that full stormwater retention on site. But it'll also help serve the surrounding areas by not adding to the flows and increasing that strain on the sanitary and stormwater system. As far as envelope, the design was primarily driven by passive house thermal and air tightness requirements. So the project team chose insulated concrete form for the assembly since it tends to be tighter than other assemblies like block and plank. Poured concrete provides that integral air barrier sandwiched between 2 layers of insulation. But while the main assembly is pretty straightforward, it's really important to review all the joints and transitions and penetrations to make sure that they're thoroughly sealed. The envelope assembly performance was designed for well above code. So the slab was R30, floor over crawl space. The roof was R33 using polyiso, and the ICF walls were R32. High performance windows were chosen with a window to wall ratio of 22% and the U value of 0.22. It was double pane windows with glass fiber reinforced UPVC frame. The solar heat gain coefficient for those windows was 0.36. So good overall performance, and that double pane window is still able to provide them that passive house level requirements. The whole building air tightness obviously was inspected along the way and then verified through blower door testing. Some insights that the project found: the Bluestone had experience building with ICF on previous projects, which really helped with the learning curve. Even though it seems really straightforward, it can be difficult to install the first time. The windows, since they had that really robust wall assembly, the project team was able to opt for those double pane windows rather than triple pane, which reduced the cost and the embodied carbon of the assemblies. Noise from the subway was reduced from the high performance windows, so that was an added bonus as well. Passive house design for passive resiliency as well. So the temperature stays comfortable throughout the year because of the thermal mass. And in the event of power outages, the building stays relatively comfortable, even though there also was emergency power on site, which we'll get to in a minute. The project team, as I mentioned, opted for that central VRF with heat recovery so that simultaneous heating and cooling was available. This is, of course, efficient solution. It's all electric. And the robust envelope meant that the smaller heating and cooling equipment could be installed to meet smaller heating and cooling loads. The savings from the reduced heating and cooling system size meant funds could be spent elsewhere. Of course, these are new technologies for tenants who might be used to heating strategies like oversized radiators and cooling strategies like window ACs. So you need to educate the tenants. Even if you feel like the system should be better for them, they need to understand how the new space conditioning equipment works, what it looks like, what it sounds like, how it's supposed to operate, so they can see what that it's meeting expectations. Projects incorporated unitized ERVs here. This was the efficient way of providing filtered fresh air. And when coupled with compartmentalization, the balanced ventilation provided by the ERVs reduced air infiltration between apartments or from corridors and decreased tenant complaints. You had fewer kind of transmission options between the apartments. Again, these are newer technologies, though. The tenants might not be used to it. Even if they're being provided better fresh air, they might not understand. So they need to know how the ERVs are supposed to look, sound, and operate, especially if the system is unitized and within their apartment. You need to clarify that the system shouldn't be turned off. The ERV is removing the stale air, providing them with fresh air, and is of course managing that moisture. So it's critical that it remains on at all times. On the maintenance side, the maintenance staff have to arrange to get into the apartments for access to filter changes. But the developer felt that this was an opportunity to conduct an overall check on the systems and check up on the tenants for this particular project. So they made it part of the full maintenance routine, part of the plan to ensure that things are in order. It was also an opportunity to clean those outdoor air intakes that need to be cleaned regularly to make sure that there's no buildup that blocks the intake. Again, making sure that there's access to those points. For water, they did choose a gas boiler with cogeneration to provide the building's DHW. Of course, they had the low flow fixtures with leak monitoring to comply with the EGC requirements and reduce water consumption. And the intention, of course, is to detect water leak issues to be addressed quickly. They also used that high efficiency plumbing layout we mentioned earlier so that they could reduce the energy consumption. Again, the traditional DHW uses a 3-pipe model with one supply, one return, and one cold water riser going to each apartment. By using a box model, the domestic hot water piping is reduced by up to 40%. So reduced piping length means reduced heating loss, means less energy to heat up the domestic hot water, which is great. Also, reduced piping length means reduced material costs. For this project for lighting and loads, of course, Energy Star appliances everywhere. There were electric stoves, electric cooking equipment, which was part of the passive house requirements. LED lighting throughout the space. They did incorporate windows in the corridors and stairs for additional daylighting opportunities and reduce the energy consumption in that way. And they were excited about the occupant health improvements by eliminating combustion in the tenant spaces. And they were excited to eliminate that fire hazard as well. Just one less risk to worry about. We mentioned the solar array. So the rooftop solar provides renewable on-site electricity production for supplemental power and also emergency power. The cogen plant produces electricity and actually is sufficient for all of the building's hot water needs and acts as a backup emergency generator to supply power to many of the life and safety systems in the building. While the project didn't actually need a generator in particular, they wanted to add one as a resiliency measure just to make sure they had a backup. For the materials, their biggest concern was durability against potential water damage as a prime factor in the building material selection. So they selected hard, non-absorptive materials for ease of cleaning and drying. And cement board, which you're usually familiar with being installed in wet areas like tubs and showering enclosures, that was installed in the lower floor to mitigate mold in the event of flooding. After the design strategies were chosen, of course, the construction documents are finalized, and then the construction process begins. And that's where it gets really fun. The project team was familiar with the passive house construction and performance testing and had used ICF in previous projects. So that was really helpful. They used the lessons learned in developing the air barrier continuity plan to develop project-specific inspection checklists so that the GC and all the subcontractors were aware of the key timelines along the way. And they performed those mock-ups to walk through any of the tricky details, any of the material sequencing requirements, and set all of the expectations up front. The successful implementation, of course, requires progress inspections and performance testing. So SWA performed those regular, Seaman Winter Associates, SWA performed those regular progress inspections throughout construction to ensure proper and consistent installation. Progress inspections are critical to ensure issues that arise are identified and addressed in a timely manner. So before performance testing. Resolving issues during performance testing is really costly and time consuming, and obviously causes more embodied carbon when you're ripping out things that you've already installed. So SWAT performed duct tightness testing, both on the in-unit HVAC ductwork and the ERV and VRF ductwork. And also verified that the ERVs were operational and confirmed airflow rates were meeting the design requirements. SWAT also performed functional testing of the MEP systems to run through and make sure that they were operating properly, and whole building blower door testing to verify airtight construction at the end, just to verify, making sure that their inspections along the way worked. So then we get to the measurement. The project team measured actual energy data to see if the building performed and lived up to its design. The performance, you can see the orange arrow points to Beach Green Dunes 1. There's a number of other passive house projects in green bars. And then there's sort of the pre-2003 and post-2003 business as usual base case buildings in gray on the left-hand side. So the bottom chart is showing site EUI, and the top chart is showing GHG emissions. So both are obviously important. The site EUI energy use intensity for the project was 34 kBTU per square foot. If you add in the renewables as well, it goes down to 29 kBTU per square foot. The building will meet the local law 97/2030 requirements for GHG emissions. As you can see in the GHG chart, the little blue line shows the emissions limits, even though its business as usual counterparts will not. And then the cost, of course. So the project, the actual annual utility costs are less than half of the baseline conventional building. When you add on the savings from the solar generation, the site's utility costs are actually a third of the conventional building. And resiliency impacts, the passive survivability meant that it maintains habitable conditions in the event of a power loss. And they actually did get tested on their flooding. So even though the entire neighborhood flooded, they were able to stay relatively dry. The building did receive a lot of awards and recognition. And so the CS Plus certification in 2018, certified under Energy Star and Enterprise Green Communities, and earned a first place award for sustainable building as part of the Queen's Chamber of Commerce, the 2018 Annual Building Awards. And of course, there were some lessons learned. So the key takeaway now for these projects can roll into the next projects. As one of the specific examples is Mark from Curtis and Ginsburg mentions in this quote that the project team was constructing Beach Green Dunes 2, the next site in the next phase, and they were informed of issues with flooding in the lobby of BGD 1. So they raised the lobby of Beach Green Dunes 2 by 1 foot during construction to make it even more resilient during that minor flooding events, which happen fairly regularly in this area. So they were able to plug in those lessons learned right away. And then on the high performance side, Crystal from Curtis and Ginsburg had some general takeaways for all of us. Owners and designers and contractors need to acknowledge the high performance target and how to get there. The design team, all of the whole team needs to give input. And we saw this a lot in your comments, like what's the most important thing? What's the most important takeaway? The design team and construction team, everybody needs to be working together to make this work. And it's definitely worth noting that Curtis and Ginsburg has gone on to complete 3 other passive house projects, 2 in construction and 1 in design. And then Bluestone also continues to use passive house as the basis of design for all of their projects, including those currently in design and construction. So it was a big hit.
Great, thanks so much, Kelly. And anyone, if questions come up, please continue to put them in the chat. But from there, we are going to wrap things up today. So this was a lot of information. Thank you so much for staying with us this morning, for participating, being active listeners throughout. Some key takeaways I just want to highlight are, a climate-ready building equals a high-performance building with resilient design strategies incorporated. So we're trying to incorporate climate mitigation and resiliency to be climate ready. High performance and climate resilient design often overlap in significant ways and have multiple benefits. Implementing climate ready building design strategies supports New York's various climate and housing goals and requirements. And IDP, the integrative design process, may be a shift from business as usual, but is critical to successfully designing, building, and operating a climate ready building. There are a ton of resources available to help you design a climate ready building. We've mentioned them throughout. We'll follow up with the links. One that we have discussed throughout is the New York City Accelerator. So with that, I'm going to pass it over to Christian to talk a little bit more about this program.
All right, thank you. Thank you, Leanne. So I'm glad to be here today to talk about our work. The New York City Accelerator is a city program to help building owners, property managers, and developers, and other decision makers work towards energy and carbon reduction goals. The program is part of the city's long-term goals to help the market transform how our buildings operate and are built. A few ways the program works in the market include providing technical assistance for building upgrades, some of which can help building stakeholders implement an electrification strategy, for instance, or maybe it's assistance with specific HVAC components, such as maybe the VRF system, which was referenced earlier in our training. We can help determine and assist with local law energy compliance. We can provide a list of vetted service providers that we can connect stakeholders with to help facilitate the design or installation of energy and carbon reduction measures. A no-cost online training platform also resides on the New York City Accelerator website, so please check that out. And lastly, an important part of the program is connecting buildings to financing opportunities and financial incentives to fund their building upgrades. Next slide, please. So how does the program work? We work with any privately owned building, 5,000 square feet or above. For smaller buildings, though, we can refer you to one of our partner organizations. So please feel free to reach out if you're uncertain of the square footage. In terms of how the program works, you would give us a call or send us an email, and we'll connect you with a dedicated account manager for your property. The account manager will provide you with objective advice customized to your needs. And the cost, the beauty of it all, it's free. There's no cost, there's no commitment. There's no requirements for participation in the program. So please feel free to reach out with any questions, any projects. We're here to assist. And the contact is on our next slide. And that's all. Thanks again, all.
Great. Thank you so much, Christian. And again, the accelerator can help with complying with the EGC requirements. So definitely utilize this great free resource that the city is offering. We also want to highlight BEX Ed. This is the Building Energy Exchange's online platform for on-demand educational content. There's plenty of on-demand content out there, so make sure you're utilizing it. There's a lot of great resources. We've had a lot of good questions in the chat around cost, about system, specifications, trying to figure out what's best for your building. So please do utilize these great resources. These are some of the links that we mentioned throughout the presentation today. We will definitely be sharing all of these resources with you. We do have a question still out in the chat. We're just confirming regarding the slides themselves, whether or not those will be shared, but all of the resources that we've mentioned today will absolutely be shared. And this is being recorded, so we can share that as well. So for some next steps, you will receive a certificate of completion for participating in today's training. This will be issued by HPD. Be sure to coordinate with your project team. So including any consultants managing the project's pre or post build submission to HPD or enterprise, in case you need to provide documentation confirming that you've attended today's training. And with that, if there were any questions that weren't answered today in the chat. It looks like we have a little bit of time, so feel free to continue typing in any questions that come up. But any questions that aren't answered today, we will definitely make sure to follow up with an FAQ and get those questions answered. And that we'll follow up with that after today's presentation, just summarizing some of these essential questions. And again, we just want to say thank you to key advisors and contributors for today's training, including Curtis and Ginsberg Architects and the New York City Accelerator, and for the hosts of today's training as well. And to all of you again for attending. Thank you so much, and we hope you have a wonderful afternoon. We can leave it open for a couple minutes, have those questions continue to come in. But with that, I think we've wrapped up.
Leanne, there are a few questions that are coming in. If there's anything that you'd like to answer live. Otherwise, I see answers are being typed by some of our other panelists as well.
All right, yeah, let's see.
There are a few questions on case studies and costs and things like that. Rather than quoting anything on the call, we'll send out all of the resources that we have. The Accelerator has a bunch of great resources around case studies, additional trainings around case studies from the field. So we will pass those along as we have them.
Claudia, we can make sure that you're added to the New York City Accelerator's email list so that you hear about future courses. In terms of HPD's courses, we will have more throughout the year. You'll also, by registering for this one, we can keep you updated, but it will be the same content. So it won't be a follow-up, but similar content so more people can attend.
Also, in regards to case studies, HPD has some really nice featured projects that you can search. I will drop the link in the chat here. So these are case studies of some featured projects, one of which we heard about today, Beach Green Dunes. And that's a great way to look at different types of projects across the boroughs and includes both new construction and preservation projects.
Great, thank you. And Jen, feel free to, if there's any questions, I see you've been actively answering a lot of questions in here. Thank you so much for getting, it looks like you're getting through to most of them, but if there's any that you just want to highlight live, if you want to unmute, feel free. Otherwise, we can follow up with an FAQ.
I think that the biggest question that has come around a couple times is whether we'd be sending slides or a video of this presentation. And I think that's Accelerator's question to answer. I think we can do it, but Natasha, can you confirm?
Absolutely, yes. We are still waiting for confirmation on that. I believe we can circulate a recording to the attendees of this webinar. We won't be making it public on our YouTube page, but we can circulate a link to that for attendees, a link to the recording for attendees today.
I know there was one other question. I know this is top of mind for a lot of folks, but from Carol Oster about added project costs. I assume that was for Beach Green Dunes. I think we had a slide talking about the incremental costs on that project, but I'm not sure.
I think
we didn't really address costs so much with that project.
Well, luckily I have that number at hand. For that project at the time it was done, and remember this was, completed a few years ago, but the incremental costs were 4 to 6% on top of what a baseline building would have been. I know that's not, the perfect answer, but it's the information that we do have. And that included the additional performance measures, additional resiliency, and so on.
Thanks, Jen. I skipped that point in the bottom of the slide there.
I can't remember. I just know we had put it out as a case study somewhere else.
Yeah, and we can absolutely follow up with that case study.
Micah Hunter had a question. Micah, you should just come back to HPD and then I can answer all of these questions for you every day. Question was, have we seen signs of costs going down for passive house construction? Yes, absolutely. As more and more products come onto the market, they're easier to get. They cost less. There's more manufacturers for a lot of the equipment. We see it especially for project teams where the architect or the owner has done passive house before. So it's, the cost gap is less every time you do it. Just in general, yeah, there's been a sense, a lot of the costs for passive house in the early days were for VRF. VRF is sort of becoming the baseline system for projects. And as we see the laws change, it doesn't necessarily mean VRF costs are going down, but the baseline that we have to compare against, which is, equipment regulations and more ambitious codes, it does compress the cost of passive house more. NYSERDA claims that the incremental cost is zero. I'm sure many people would contest that. But I think in some cases with a really good integrative design process, that can be true. And stay tuned. We might be able to help project teams reduce costs even further at HPD. And last question, Carol, I'm going back to your question. The 4 to 6% incremental cost was construction cost. I don't have a graphic to show you. But that is from a different presentation, and that was definitely construction costs. And as for solar, the tax credits under the IRA have become incredibly rich, especially for affordable housing. So in addition to the fact that, costs have been coming down over the years, solar has become even more affordable. I think that's it. It's 12:29. Thanks for those of you who stayed after school to answer questions or to ask questions.
Yep, thanks so much. Really enjoyed spending the morning with you all. And thanks, Jen, and again to the Accelerator for hosting today.
Thanks, everyone.
Thanks, panelists.
Thanks, everyone.
Thank you.